So we want to find out if this transformation, this linear transformation from P1 back into itself is injective or surjective. So the best way we could do that is probably to actually try to figure out a little bit more about this transformation. So what we're told is that T of an arbitrary P is P0 of X plus P1 as a constant. So we could maybe write this a little bit nicer kind of in terms of a generic polynomial. Let's say P of X, we can write all polynomials in P1 as AX plus B, or you can use MX plus B if you like, but AX plus B is kind of nice for linear algebra. So if I want to rewrite this thing up here, I should find out what P of 0 is. Well, that's A times 0 plus B, which is B. And P of 1 is A times 1 plus B, which is A plus B. So what my polynomial here is my polynomial transformation is P of AX plus B, which is a way to describe all polynomials in P1, can be written as basically BX plus A plus B as a constant. So if you want to find out if it's injective, basically we are trying to see if two polynomials, so let's say if I have P and Q, if T of P equals T of Q, so if it's injective, the only way that this happens is if P equals Q, because you can't have two different polynomials mapped to the same place. That's what injective means. So if you have two polynomials mapping to the same place, it must actually mean that they're the same thing. So yeah, that's what we're going to do is let's just take arbitrary polynomials P and Q. So let's say that T of, if we have AX plus B is going to be BX plus A plus B. And if I follow the same rule for, let's say, Q, I'm just going to define Q to be, let's say, CX plus D. Then that's going to be DX plus C plus D. And so if these two things are equal, so if T of P equals T of Q, well, this means that BX plus A plus B equals DX plus C plus D, and that's for all X values. So basically the X coefficients tell us that B must equal to D, and from the constants, we have that A plus B must be equal to C plus D, but since B and D are the same, that implies that A equals C. And if B and D are the same and A and C are the same, then that means that P must equal Q. So it's injective. So if we want to show that it's surjective, I'm going to take this and shrink it down so I have a bit more space. Okay, so I want to show that it's now surjective. Then what I need to show is that for any polynomial, so for any Q in the codomain, which is P1, both the domain and the codomain, there is some P in the domain, which is also P1, that maps to it. So again, if Q equals, or if Q of X is CX plus D, then can I find a T of P of X that equals CX plus D? So if I'm using the same definition for T above of for P of AX plus B, is it possible to get this somehow? I follow the map T, and what that does, I've already sort of defined that to be bx plus a plus b equals cx plus d. And so here, basically what I can see is I'll just let bx equals cx. I need this to be true. So b must be equal to c. And so for any c, I'm just going to let b equal that c. And then for the constants, I need that a plus b equals d in this case. And that means that my a is d minus b, or d minus c. And so for any dc, I'm going to let b be c and a equal d minus c, so that t of ax plus b actually maps to my q polynomial. And that's sort of what I found there. So therefore, it's also surjective. So it's both.